Okay, before we start, I think I'll introduce our speaker, Jason Keeler, today. So Jason comes to us on his sabbatical after recently getting promoted to Associate Professor of Meteorology at Central Michigan University. He's been there since 2018 and joined the faculty at CMU following postdoc studies at the University of Nebraska-Lincoln and graduate studies at the University of Illinois at Urbana-Champaign, and has done undergraduate at SUNY Oswego, so is familiar with our lakes in general, of course. From his background I'm reading, his research blends aspects of boundary layer and mesoscale dynamics with a focus on destabilization and evolution of convection, often applied to the coastal areas. And before I let Jason come up here and speak about the awesome campaign that he did this past summer, is that Jason and I met about 8 years ago, and where he was a postdoc at Nebraska and I was a PhD student at Texas Tech, and we were storm chasing on a field program together. So Jason continued with his operational or observational studies while I moved a little more in the modeling realm, but I'm very excited to have Jason come speak to everyone here today. So without ado, I'll let Jason move forward. Thanks.
Thank you, Abby, and thank you all for hosting me here today. I'm excited to talk with you about some of the recent work that I've been doing in my group with a focus on the maritime to inland transitions towards environments for convection initiation or MITTEN-CI field campaign. Always happy to come up with a good acronym, and it feels like that's a big chunk of the funding. So glad I had the team to help me come up with that. There we go. So I know we've got a broad, diverse audience in terms of all of our backgrounds here. So I'm going to start with some background and motivation, discussing a little bit more detail on some of the meteorology behind sea or lake breezes and some of the things we're studying relevant to convection. Moving on from there, the primary focus will be on the MITTEN-CI field campaign, and I'll show you some of the preliminary analysis that we have, in addition to discussing just the broader aspects of the campaign, the types of observations that we have, and what we hope to achieve with that. Since we're a little bit earlier in our analysis of the field campaign data, I'll also be talking with you all about some idealized modeling studies that we've done, looking at the dynamics of lake breezes and how that relates to convection initiation or development of thunderstorms. Finally, being in GLERL, I want to talk a little bit about some observational opportunities and how we can add to our observational network to improve our knowledge of the Great Lakes system. Before getting into the main part of the talk here, I do want to acknowledge the broad group of collaborators and institutions that have supported being able to make this research possible, starting with the grad students who are doing a large chunk of work in chewing up and, well, not chewing up, sorting through the data from MITTEN-CI and helping us to really understand it. So Kyle Brooks, my own student at Central Michigan University, Cassie Eisenberger, who's a recent alum of CMU, who's now at Texas Tech. Recent group alumni, Christian Boyer, who did his PhD in my group, Brian Approsi, who's now a grad student at OU. And then you come to all of us faculty and researchers on the campaign here, just acknowledging the broad collaborations there with Dave, Junming, Chris, Brian, Heiss, and Adam. NSF has supported this work. NCAR helped us out with the Earth Observing Lab and has the field catalog for this. Some of the supercomputing that we've done has been through Access. Of course, acknowledging Sigler, of which CMU is a consortium member, I believe is the correct term. Yes, I got it. And then also the Grand Rapids Weather Service Forecast Office. And in general, I just want to acknowledge the broad support that our group has had from employees of federal agencies and how important it is to have that support and those members at full force. In terms of our background and motivation here, starting off with a nice picture of from the MITTEN-CI field campaign. that line of shallow cumulus you could see in the background there is the visible indication of the presence of the lake breeze front on that day. Now, some of that background on just general thunderstorm information here, we want to assess the impact that Lake Michigan has on convection initiation or thunderstorm development. And to do this, we really need to think about the classic ingredients that we think of that ingredients-based approach to thunderstorm development. Now, the first is the most intuitive. We need moisture. We're forming clouds, precipitation, and so we're interested in the lake's role in the moisture content in the lower atmosphere. Instability, even if you're a non-meteorologist, you've heard your TV meteorologist talking about it being very unstable on a particular day. What instability means is just that there's the potential for there to be some integrated buoyancy over the depth of the lower atmosphere that leads to there being some updrafts that can help to develop those thunderstorms. And that instability is tied also to moisture in some way, and so we'll come back to that a little bit more later. And then finally, lift. Even though thunderstorms develop in an environment that does have some of that buoyancy, oftentimes in lower levels of the atmosphere there's some inhibition to that, and you require some amount of lift to overcome that lower level inhibition so you could actually go ahead and form deep moist convection or thunderstorms. Now, all of these ingredients are going to be affected by large bodies of water. And a lot of this is rooted in the temperature of the water itself. And so showing the last, I believe, 30 years worth of Lake Michigan lake surface temperatures and looking at how that varies over the course of the year. Now, we're in the time of year now where the lake tends to be warmer than the air over that, and so that aids in convection. All this lake effect snow that we've been seeing in recent days here is, we're in prime season for that. Now, given that we had a low of -9 Fahrenheit in Ann Arbor this morning, I'm going to help you out by shifting over to the warm season. And you can at least imagine that it's in the 80s outside right now. Now, during that season, when the lake is cooler than the air that's passing out over that in our spring and summer months, that air is going to be cooled. And so that actually is going to be a stabilizing influence that could hinder thunderstorm development. And so what we're interested in is air that is displaced from over the lake to over land. How does that air moderate its temperature over time and with distance inland? And how does that affect the favorability for thunderstorm development? Another substantial impact here is on the development of sea or lake breezes. And so we have a classic schematic up there of what that looks like. And this arises from the air over the lake itself being colder. But then during the day, the air is going to become increasingly warmer. Are we still good?
No, it's not advancing online. Oh. Now let's try this. All right.
Both are. All right, we're good.
Okay.
All right, thank you. Okay, so now that all of you online can actually see what I'm talking about, let's come back to that schematic on the right side there. And so when the air over the lake itself is cooler during those warm season months, over the course of the day, the air over land, of course, is going to become increasingly warm. And because of that warm air over land, that thickness of a layer in between two pressure surfaces is going to increase. And as a result, we end up aloft having an offshore directed pressure gradient force and near the surface an onshore directed pressure gradient force, which over time is going to cause us to get that full circulation there. Now, at the leading edge of that circulation, we're going to have what's called a sea or a lake breeze front. This is a nice kind of 3D schematic here where we can see that cooler air shaded in blue. We see that it has some perturbations to the top of that. Not going to get too deep into that just yet, but at the leading edge of that, we have that lake or sea breeze front. And as a result of the convergence that you get at that front through mass continuity, we're going to have ascent. And that's your source of lift and way that the lake breeze front can help to aid in convection initiation. Getting slightly more complicated here, the way that the lake breeze front interacts with the large-scale flow is going to affect how well defined or how poorly defined that lake breeze front is. On the left, I have a visible satellite image from a day when there was large-scale offshore flow. I'm going to color code some of these vectors that I'm showing based on what the temperature is. So we've got relatively warm offshore flow. And with that, I'm going to impede the inland progression of that lake modified air. And that results in a really well-defined lake breeze front. So we see that very sharp boundary from clouds to clear by the lake. That onshore flow associated with the lake breeze there, I've color shaded that from blue being relatively cool to moderating as that works its way inland. So nice clear-cut lake breeze front. I could see in the southern portion of that diagram there that some thunderstorms have developed. In contrast, when I have large-scale onshore flow, I might not get as well developed of a lake breeze front, or I might not even be able to discern the presence of a lake breeze front there. But I still do have that gradual destabilization, and you can see that area a little bit further inland through, say, here, where the cumulus field does seem a little bit agitated, even though it's not as clear-cut. There could be something there. Now that we have some of the lake breeze basics, I want to talk a little bit more about some of the specific, maybe more complex things that we're interested in learning about through MITTEN-CI. One of those is dealing with entrainment that we can have from ambient air, either into the boundary layer overall or into the onshore flow associated with the lake breeze. Now, I've got some Doppler LiDAR measurements here from some preliminary field work that we did in summer of 2021 with the University of Illinois. And on the left there, this is some range height indicator scans with the Doppler LiDAR, with the left side of that being closer to the lake and the right side being further inland. And we see with those black vertical lines there, this blue shading being flowed towards the LiDAR, red shading being away. So I could see this circulation associated with that lake breeze there that over time makes its way further inland and appears to be deeper as it's approaching the location of the LiDAR right there. I can also see on the right, the Doppler LiDAR was operating what's called a stair scan. It was pointing straight up. And so we were able to measure the vertical component of motion there. And so I could see in the time before the lake breeze front arrived at the location, some broader areas of ascent in red or descent in blue. And then after that lake breeze front came through, much more fine-scale turbulent motions that we're seeing even within that onshore flow component of the lake breeze front there. But in general, what we want to consider is, I've got that surface sensible and latent heat flux. This inland displaced air is also going to be moderated based on what's above it. And so you could have a case where that inland displaced air is being warmed through heat fluxes and convection at lower levels, but also through entrainment at the top. And how this evolves, whether it's the onshore flow of the lake breeze or a just less well-defined case where it's just entrainment into the boundary layer, all of this is going to affect the convective environment that we have for storms to potentially form in. Getting a little bit more complicated, there's something that is very near and dear to my heart. And this is something that everyone or most people are used to thinking that if the temperature is cooler, it means it's less favorable for thunderstorms. And by focusing solely on that, we're ignoring the importance of moisture in determining how buoyant air can become. And so if I have an air mass boundary, so a boundary between two separate air masses, if the cooler air mass is only slightly cooler than it is on the warm side of that air mass boundary, but the cool air mass has much more moisture content, that cooler air can actually become more buoyant than the warmer air. So it's counterintuitive, which makes it fun. And so we of course came up with a nice acronym for this. Actually, I give credit to my collaborators at University of Nebraska for coming up with this acronym, calling it a mesoscale air mass with high theta E, or a MAT, where theta E is just for the variable equivalent potential temperature, which for the non-meteorologist is just a measure of both the temperature and moisture content within air. And so we use theta E as a measure for buoyancy because if the temperature profile aloft is the same in two locations, having higher theta E at the surface means you also have more CAPE, or more instability present. We care about this because it affects the way that thunderstorms evolve in these environments. There are some classic cases back in the 90s during a field campaign in the Texas Panhandle that showed that thunderstorms that interacted with mat air produced tornadoes, while the other thunderstorms on that day did not. The former world record hailstorm in Aurora, Nebraska, I believe that was an 8-inch diameter hailstone, and that was a storm that crossed into one of these mats and was able to ingest that air and affect how that storm evolved. So we care about this. Just showing visually here how, for those of you familiar with SKU-T diagrams, the black profile is within the mat and the gray profile is in the ambient environment. So you could see how if it's only slightly cooler but much more moist, we could end up having greater CAPE. And I promise this is about as deep as we get into some of the more technical things here, but I want you to understand this when we get to that later in the talk. We're going to bring this back to some physics basics and talk about entropy here, because this change of entropy is what's going to actually change that equivalent potential temperature. And so we can have these changes because of advection into an air mass, precipitation evaporating into that air mass, solar insolation, or surface latent and sensible heat flux. And I want to remind you that we're not just, for the advection term, we're not just talking about horizontal advection, we can also be talking about vertical advection. And that's going to become a critical point later on. In the interest of time, I think I'll come back to that schematic later, because I know I'm spending a little bit more time than I intended on background here. In terms of our large-scale flow and how lake breezes might evolve in conditions of large-scale onshore flow here, I have that diagram from earlier again on there showing this evolution from having there being fewer small cumulus clouds, there being some larger cumulus clouds, indicative that maybe there's something going on there in terms of an embedded lake breeze front. Now, our classic modeling studies going back to the 90s suggested that you would not get discernible sea breeze fronts under large-scale onshore flow conditions. However, some campaigns, field campaigns from around the same time, showed that through careful analysis you could actually tease out that detail, that there was in fact some embedded circulation related to the sea breeze. In terms of other observational studies, some satellite-based studies, some of those performed in the Great Lakes region, have shown that you can actually detect some sort of discernible boundary. And so just focusing again in this area where this was before the campaign, we don't actually have other data from this day, but there's some indication that there might be some enhanced cumulus field in that area. And so what I'm getting at here is that there's value in learning about this and revisiting this with the type of data you could get in the field to look at this, but also in, say, an idealized modeling framework. Other things that we want to consider here is how the environment interacts with that lake breeze front. We had talked about that being that source of lift, but it turns out, and we've known this since the late 80s, that with thunderstorm outflow air masses, which are going to have a similar density current-like structure, we can end up having the vertical wind shear affecting how air interacts with that air mass boundary. And so I want you to focus on that lower right portion here, where those vectors on the right indicate that change in wind with height. And I can imagine in an environment with that type of wind field, I'm going to create that sense of rotation that we see there. Within this thunderstorm outflow, or potentially applied to a lake breeze, I'm going to have that opposite sense of rotation. And by having that opposite sense of rotation, it favors more upright motion at that front. And so this is RKW theory from a paper back in the late 80s. And part of what we want to look at is how this could apply. Just some other examples of what these density currents might look like from Hudson et al. Had to get one citation for my host here. Looking at some of these outflow cases from, I believe these were supercells, but a similar type of structure where you can see this nice density current-like structure there. And we want to think about how the vertical wind shear in these lake breeze cases affects that structure and how that affects the ability of this lake breeze front to initiate convection. Finally, another aspect we want to look at is how different areas, localized areas of rotation or vorticity can develop along the lake breeze fronts and how that might affect convection initiation. Now this example is from a dry line, and we see in there the color shading is the radar reflectivity, and those thin black contours are indicating those vortices or areas of rotation that you have along that. And you could almost see in the lower left portion of that there's this almost honeycomb-like structure or open cell convection structure there. And where those open cells interact or intersect with that front is where you get a lot of those vortices. And so these mesoscale vortices or smaller scale vortices can travel along that boundary, and especially where you have those different inflections. And if they can merge, they can further change the shape of that inflection and can really aid in ascent in those areas. And so in terms of our broader background here, what I hope to accomplish is to show you that, yes, there's these lake breeze basics that we've understood for decades, but there are a number of different things that we need to consider about how the thermodynamic environment can vary near these lake breeze fronts, and how the kinematic environment can vary near these fronts, and how all of that together are the things we need to understand when it comes to lake breeze fronts initiating convection. So overall, there's substantial value in a data set that can quantify surface fluxes or turbulent exchange between lake-modified air and the ambient environment, thermodynamic and kinematic evolution of air that started out over Lake Michigan and was displaced inland, and looking at how that evolves both with space and in time. And then really we need observations out over the lake. That is in terms of the vertical profile of thermodynamics and kinematics, because that's our limitation in terms of the operational observational network. And so we had the MITTEN-CI field campaign, and we had a broad range of instrumentation for this. And I'll get into a little bit more detail on each of these individual instruments in just a couple slides here. We had this campaign was in July 2024. We operated primarily in the Holland to Lansing area with 37 team members, 28 students, and 9 of them from CMU, 5 universities. And we had these instruments, again, in that roughly 120 kilometer area. So we could have this nice, almost 2D view of the atmosphere. Getting back to this image, in terms of our instruments, we had 2 mobile radars, 2 mobile mesonets, and so that being a less common instrument platform, it's an instrumented SUV where we could have pressure, temperature, humidity, and wind measurements as we're driving across whatever it is that we're studying. We had a Doppler LiDAR. You could kind of see there's a small drone. That's the Coptersonde 3 that was used for this. Full tropospheric radiosondes. Not pictured, we also had mobile radiosondes that we were able to launch at multiple points, working our way inland along the same path that the mobile mesonets were driving. And then not pictured here, we had an array of flux towers. In terms of some of those instruments were a bit covered up, so you can have a broader view of what these look like. These are the Texas Tech Ka-band mobile radars. We see scanning there with a couple, trying to be more vigorous cumulus clouds in the background there. Closer view of the mobile mesonet and what that looks like on the inside here, where we're able to, have internet access, communicate with other vehicles in the field, watch the data coming in live there. And then finally, for our mobile radiosonde team, this is using the wind sondes that are produced by Sparv Embedded in Sweden. And we had this set up so that students could launch these instruments. That balloon is conveniently right in front of a cloud, so I've highlighted that for you. And so we were able to launch these very easily as we worked our way inland to get an idea of how that convective environment varied over short distances. We had a very, at least our initial idealized view of what this might look like. Just in general, just to save us on time here, this is just a broader view of how we might deploy a lot of our instruments along that kind of cross section there, closer to the shore, if I have offshore flow conditions, and how we could stretch out, at least in terms of our mobile assets, where they were if I had large-scale onshore flow. What I will say is during the field campaign, we probably went with that top view quite a bit more frequently than the bottom view, just because of the cases that we were presented with in the field. Typical day, the great way to tempt fate is to come up with a plan. And so we varied quite a bit from this, day to day during the field campaign. But in general, we had these more intensive periods with data collection within a given day, where we wanted to operate for a few hours, give people a chance to reset and reconsider how we're operating, and then go again for another one or two more times over the course of the day. Where during one of those windows, we might say, drive our mobile assets inland and then back to the shore again. I mentioned that we focused on the Holland to Lansing area. We focused in on that area because we avoided urban heat islands associated with Grand Rapids and Lansing. And if you can squint, you can kind of see that we miss out on some trees by being in that particular area too, which is important for our radar operations. We're also far enough north that air is passing over a larger fetch of Lake Michigan, as opposed to being so far south that the air is barely modified. We chose July because it had a favorable wind climatology in terms of, this is a wind rose, just you can imagine this being a measure of how frequently you have wind from given directions. And we see peaks in wind from the southwest and also from the east. And so we're expecting this range in flow regimes where we could have large-scale onshore flow or also large-scale offshore flow to give us a range in different types of lake breeze fronts. And so we have this period where we shift a bit in terms of winds. Also coincides with the period of warming of Lake Michigan. So we could have much cooler earlier in this period and quite a bit warmer by the end on average. Now, I think we all know in this room that Lake Michigan was quite a bit warmer than average last summer. And so this is around the middle of the campaign where we see that Lake Michigan is well into those low 20s Celsius in terms of the water surface temperatures. And this does affect the nature of lake breeze fronts that we get. That we did tend to have a little bit more, or we had more days with diffusely defined or poorly defined lake breeze fronts, which ends up being quite interesting for us. For those of you in the room interested in upwelling, we had at least one case where there wasn't much of a defined lake breeze front. An upwelling event occurred, and then within an hour, a well-defined lake breeze front developed and started to make its way inland. So these things that happen on small space and time scales matter. We also had a period of time where it ended up being a little bit cooler following the remnants of a hurricane. We weren't exactly expecting that in July. But again, we were flexible enough in our operations plan that we were able to accommodate for all of these things. So looking at the overview of what types of cases did we get over the course of this month here. Within that month, we managed to have 21 dates with operations. One of those dates, we had kind of 2 primary missions. So really, if you look at this in total, we had 22 different missions within that month. Wide range in how well-defined lake breeze fronts were, from very clearly discernible to cases where there wasn't much of a temperature gradient, but there was a difference in boundary layer structure that occurred and make its way further inland. At least 5 of these developed into those lake breeze mats, those cases where you have more instability on the cool side of the lake breeze front. A few other cases of special interest. So I mentioned the upwelling event. We had a lake breeze front that was overtaken by a synoptic-scale cold front going through the area. And then for the vorticity nerds in the room, we had some lake breeze front misovortices that exhibited the Fujiwara effect of 2 vortices in close proximity that rotate around each other. So plenty for us to dig into in terms of the data that we have and how that related to the potential for convection initiation. That said, the going joke in MITTEN-CI is that we had a lot of mitten and not a lot of CI. But there's still a lot that we can learn about in terms of boundary layer structure and from the few cases of convection initiation that we did actually get in the campaign. So I'll start out in terms of actual observations from the campaign. This is from the copter sondes. These are drone flights that were operated about 300 feet out, or 300 meters rather, out over Lake Michigan, and gave us that baseline, at least when there was onshore flow, in terms of what the boundary layer was like before that air came inland. Now, on this case, we started out the day with offshore flow. So if you look on the left there, this is time increasing from left to right, and then with height above sea level there. And so we can see this is a theta. You could think of this as being related to temperature, where we have this cooling that developed at low levels as the day went on, and that's from that lake-modified air being displaced inland. Looking at this in terms of our water vapor mixing ratio, we see that at that same time that it cooled, our moisture content increased quite a bit. So we had that air that had been moistened by Lake Michigan. And then in terms of wind speed, we also see that wind speed had increased as time went on as well. I don't have this to show today, but we do know also that the wind direction became onshore at those times. So a nice way that we could look at how the lower portion of the boundary layer evolved over the course of the day. In terms of some of our Doppler LiDAR observations, so again, in this case, we're looking at flow. So these are looking at areas of blue going towards the LiDAR, which is at the center location, and red going inland. Again, lake to the left, inland to the right. And so I see this broad onshore flow there, but if you look carefully, down near the bottom here, we see this area of enhanced onshore flow. So large-scale onshore flow with an embedded lake breeze within that. In terms of some of our mobile mesonet observations, this is from transect working from left to right is going inland. And so I see that I have this slight warming that happens right at this location here. I also have wind vectors on there. So I see this offshore flow, onshore flow. That's our convergence lined up with that cooling. So that's our lake breeze front. If I look at dew point, you see just how much the dew point increased as you went onto the cool side of the lake breeze front. And then our equivalent potential temperature, again, in some ways a measure of instability, showing that our highest theta E or greatest instability was actually on the cool side of that lake breeze front. I've overlaid some of our other mobile mesonet observations on visible satellites. This is also some surface theta E here, where I can see this nice, clearly defined lake breeze front through there with the highest theta E air on that cool side closer to the lake. What I love about being out there in the field is that we can look at pictures from this same time here. And so in terms of what we were seeing in the mobile mesonet when we were gathering this data, we see this really nicely defined line of cumulus associated with that lake breeze front there. Further inland on this day, there was some open cell convection, and so you could actually make out in some ways the rings of convection that you had going on. So it's really nice. As an educator, it makes me excited when I could see things that could really show visually what we could see in data otherwise. A contrasting case here that also had higher theta E on the lake side of the lake breeze front, but also just showing that in this case we had a much more isolated line of cumulus along the lake breeze front as opposed to a more widespread cloud field, which in person looked like this, with our ever important good luck charm of the cloud-shaped stress ball on our dashboard there. Now, in terms of the wind sonde observations that we had, so these are some just interpolated observations there where I had soundings at the left and right edges, but also where I have those dashed lines there, just showing the depth and horizontal extent of that higher theta E air associated with that lake breeze there. So again, just showing at least some preliminary views of some of the features that we were interested in from the campaign. Now, those soundings, I should go back for a second here, we're really only showing them up to, or within that boundary layer. But for broader context, we also had our full tropospheric soundings. And so we could see, how that broader environment evolved, but you could also see at very low levels that slight bit of cooling right down by the surface. And this sounding, I should say, was launched, if you're familiar with the Holland area, this is that tunnel park. So right by the lakeshore there, which is also where we had one of our flux tower sites. Speaking of the flux towers, I'm showing you from a few different locations on the same day how our temperature shown in red there, wind barbs, and also our sensible heat flux in black there. And not surprisingly, at our shore locations, that top panel there, we see that massive spike in heat flux because that is when the lake breeze developed and we had air that had not yet been modified by the land passing over. I believe the flux tower was on a dune. So you can imagine just the large amount of heat flux you're getting as that air is first displaced out over land. We don't see that spike quite as much when that lake breeze front made it. This is 20 kilometers further inland, but you still do see that cooling that you get. By the time we are 30 kilometers inland, again, we see that cooling, not quite as much. We do have this one peak in heat flux after that. And then even further inland, the lake breeze front didn't make it to that point on that day. And finally, we have some of our radar data. So Ka radars are very sensitive, and so Cassie is working very hard at filtering a lot of this. Abby can feel her pain. But for now, we do have these nice views of some of those scans where you can see through here the enhanced reflectivity associated with that lake breeze front. And in terms of our radial velocities, red being flow away from the radar, blue being towards it, so we could see that convergence associated with that radar fine line in there. And so there'll be quite a bit more in terms of what we have from these different data sets. Looking forward here, so again, we're early in our analysis, but it's clear that we have a nice diversity of cases in terms of their evolutions. And with our broader impacts, the type of data that we have is, can lend itself to just broader understanding of convection initiation or boundary layer evolution. And finally, we have this potential here to improve maybe parameterization of heat flux or boundary layer type processes as we go forward beyond the campaign. Just getting a sense, how are we on time here? Because I know we had a couple. We're good. Okay, thank you. All right, so that's what we had in terms of the campaign itself. I do want to spend a little bit of time talking about some complementary idealized modeling that we've done related to this. Really focused in on those lake breeze mats here. So we were using the CM1 model, running some large eddy simulations. We had a horizontal grid spacing of 100 meters here. And within that, we were focusing on this domain that had water in the western 50 kilometers, land in the remaining portion. This is a pseudo 2D domain, so we're only about 20 kilometers north-south. To have realistic boundary layer structures, we included friction and radiation and surface fluxes that allowed us to develop realistic eddies within this environment. And speaking of eddies, we used something called eddy recycling to make sure that we didn't have eddy deficient areas where there was inflow into the domain. Happy to talk, that's pretty technical there, happy to talk with modelers who are more interested in using that outside of the talk. For our initial conditions, these were relatively long simulations, 12 hours going from 6 a.m. to 6 p.m. local time. And so you might be looking at that saying, well, if you're studying convection, why is there so much sin at the start of the simulation? It's because it was 6 a.m. We needed this environment to be able to evolve towards something where convection initiation could happen and give the lake breeze enough time to develop within this environment before you had convection initiation occurring throughout the area, regardless of the front. So starting out stable, I wanted to really focus on the cross-shore wind component here. And so we set the north-south component of the wind to 0 throughout the domain. We varied the base state zonal or west-east component of the wind, as I'll discuss on the next slide here. But on top of those background values, I also had some vertical wind shear in that area, as you would expect in more of borderline severe storm convective environments. So this is a broader parameter study, and so we varied the cross-shore wind component from offshore flow of 5 meters per second to calm to onshore flow of 5 meters per second. I'm going to focus only on the offshore to calm conditions for the information that I show you here today. We also varied the date associated with radiative forcing and the lake temperatures. So we get an idea of how this changes over that June, July, August time period when you're starting to get more and more lake breeze fronts to develop. And then finally, we also varied the lake surface temperature percentile for those individual dates there. So we can get an idea of how does this evolve when the lake is near normal, cooler than normal, warmer than normal. And so again, I'll just be focusing on the calm to offshore cases here. Now, I'm going to be talking about how the perturbations to theta E were on the cool side of that lake breeze front in these cases. And so to do that, we had to develop our way of quantifying what that was. And so we had a method that we used to identify our lake breeze front location. I should say here we're looking at west to the left, east to the right, and I've got this equivalent potential temperature that is lower here, jumps up at the lake breeze front, and drops off. This being an example of a map there. So I identified that frontal location, looked inland of that, and calculated the mean theta E just to get an idea of what the background value was. Found how far back I had to go for theta E to decrease back to the environmental level, and then consider that area the map. And so within that area, I could then calculate the mean theta E and the difference between that and the ambient environment. So this, the calculus folks in here will be excited about mean value theorem. So we're just calculating the mean of this perturbation within that area, and using that as a way to approximate the magnitude of that mat there. Now, I've got some heat maps here that are over our parameter space for this study, where you'll note that I have that background flow is what I have changing top to bottom there. So 0 being calm, negative 2.5 being weakly offshore, and negative 5 being more strongly offshore. I also look at columns within these of June, July, August. And then finally, each of these individual subplots is for a given water surface temperature percentile. And so I can look at a large number of simulations together in this case. And I should say that I'm looking at each of these individual simulations at a time before any thunderstorms developed in any of them, because I want a common comparison point for those. And so looking at that, I can see that I have these greater theta E perturbations or more defined mats when the base state flow is calm. I also have slightly stronger mats when I have June radiative forcing as opposed to July or August. And then ever so slightly more pronounced when I have a warmer lake, comparing that mean theta E perturbation for the 25th percentile versus the 90th percentile there. And so what I want to do is focus in on a few of these. So just since we had a smaller difference varying the lake surface temperature, I'm focusing on just this 50th percentile temperature and want to look at what happens in these 3 individual simulations there. And looking at those 3 simulations, what I wanted to do is take those wind, radiation, and lake temperature combinations and vary a few different things. First, I want to really cool down the lake and cool it down to the 10th percentile and see if having a much cooler lake has much of an impact. I also want to change the amount of moisture that is present above the boundary layer. And this is going back to the start of the talk when I was talking about mats and said that we were dealing with vertical advection of theta E being important. Now, if I have a particularly dry environment above the boundary layer, that's going to be some low theta E air that by having more vigorous thermals, I can tap into that and actually dry out the boundary layer inland. Okay, thank you. And so that's something that we want to vary there to see how much of an impact that has. And we could also do both. And so in terms of the different soundings, just showing you what those looked like. The original sounding is in the middle. Our dry sounding on the right there, we really dried that out. And then moistened up above the boundary layer in this case here. So by doing that, we had a slight difference for that 10th percentile one. We kind of dropped that down from 0.18 to 0.05, more or less got rid of the mat or kind of neutralized that. But the big differences that we have, if you look left to right in here, are by whether we had that dry air above the boundary layer or moist air above the boundary layer. That was the big difference that we saw there. These differences, so we've got ranging from 0.5 Kelvin on average to over 2.5 Kelvin with a dry profile. Looking at these slightly differently, I can look at in individual simulations what was the theta E perturbation before any thunderstorms developed in that environment. Because if I have more moisture above the boundary layer, I'm going to develop storms earlier. And if it's drier above that, I might develop storms later. And so I want to see what happens before storms develop in those individual simulations. And in this case, it's much more dramatic in terms of what we see with the moisture there, where only 0.68 Kelvin for moist, but now over a 5 Kelvin perturbation for the dry air. And I'll remind you that we're looking at the mean difference. And so you could think of, across the front itself, a ballpark of a 10 Kelvin theta E difference, which in terms of CAPE, for those of you who are more familiar with this, we might be dealing with something in the ballpark of several hundred or over 1,000 joules per kilogram difference in terms of CAPE. So overall, MATs are favored with a calm base state flow. A greater inland penetration can help to explain this, because if I have less opposing flow, that lake breeze front will make it further inland, which means it's getting modified more because it's passing over more of that warm ground. They're also more pronounced in June. That makes sense because I'm going to have greater radiative forcing, which is going to help to drive those thermals and help to mix down any dry air that may be there. But really, it's that presence of decreased moisture above the boundary layer that seems to be the primary driving factor, at least in terms of lake breeze mats here. And as I mentioned before, having more moisture above the boundary layer helps for there to be CI earlier, which even prevents there being enough time for the mat to potentially develop. Now, I'm going to bring things back to being accessible for everyone. Thank you for indulging the meteorologist in the room on that last bit there. How do we think about observing these systems operationally, potentially? And I purposefully picked this image where we're looking from lake towards land with that one distant thunderstorm there. It's really over the lake itself where we need these observations. The buoy network that we have is extremely helpful, but we need that vertical component as well. If we want to understand instability or stability, that is a necessary component to really get at that. And so hopefully we can start to have some conversations about how we might be able to do that. In terms of broader concluding remarks here, sea and lake breezes are one of the most studied type of phenomena. I think I looked up, there's over 5,000 AMS journal articles that mention sea breeze or lake breeze. But I hope I've convinced you that there's still more for us to learn here, and that those heterogeneities in convective parameters related to mats or other things, their 3D structure is something that we can learn more about through these field observations, how they interact with their environment. There we go. And then the MITTEN-CI dataset does have the potential to help us out in these areas. Idealized simulations can play a role as well, as we showed in that parameter study, and we were able to learn more about mats and mat development through that. But overall, further work is needed to understand how do air parcels from that mat end up in thunderstorms, or do they or don't they? Is this a thermodynamic interest, or is it actually meaningful in terms of how these storms evolve? And that's outstanding work at this point. And finally, MITTEN-CI allows us an opportunity to evaluate what impact having these increased observations in this area could have in our warm season forecasting capabilities. With that, I'm happy to take any questions that you might have.
Does anyone in the room have any questions? Oh, go ahead, David.
Thank you. Excellent talk, Jason. Really great information. I'm wondering, you're still digging into a lot of this data. This is sort of just the first glance. I was wondering how much you've looked at sort of the 3D structure of the lake breeze itself. And is there any, we kind of think of it as sort of a binary, lake breeze is there, lake breeze is not. Is there any sort of like uniqueness or sort of difference in sort of the characteristics maybe you've noticed early on or hoping to see in your data?
So in terms of the 3D structures of that, I mean, I know there were, I think one of the things that we found interesting is how smooth the front can be on some days, and how perturbed it can be on others. It's not some uniform, here's the structure of the lake breeze front. We had days where it was really tight and well defined, and days where maybe you just transitioned from open cell convection to convective rolls, and that was the lake breeze front. And so I think there's a lot to be learned in terms of the structure and how that varies day to day or even over the course of a day.
My question is, the theory and modeling are very good here, and how this theory and the modeling, theoretic or idealized modeling, can apply to the realistic forecast. Now, forecast is pretty 3 days forecast are usually very good. However, for the thunderstorm, for the convection, maybe not. So someone had done this kind of the short-term prediction for the lake and lands interaction.
So just to summarize, so you're interested in the applicability of the idealized simulations to forecasting? So I guess what I would say there, I wouldn't necessarily use them as like a lookup table of this is the closest condition we have to this simulation within the parameter study, but instead I think its application is more in the lake is warmer than normal during this time period. Here's how we think that might affect convective environments. Or maybe, if I have a pronounced elevated mixed layer above the boundary layer, I know that a lake breeze mat is maybe more likely than not. And maybe I need to be a little bit more careful about assuming that thunderstorms will only develop further inland and not necessarily closer to the lake.
Jason, I have 2 questions. The first one is based on the distance inland. So you have the Holland to Grand Rapids, and I'm just curious, compared to maybe other studies as well, like how far inland, are those lake breezes able to develop that convective initiation? And then my next question, because I know that NWS was one of your partners, and it kind of piggybacks off the question that Gia was asking, but how you kind of framed all the background, kind of motivation for the work, and I'm just curious from a forecasting perspective, if this is a specific area that we're not doing very well at in terms of forecasting, like what kind of feedback from those NWS partners did you get in terms of developing the study and kind of next steps? Thanks.
Yeah, and so for the first question in terms of how far inland the lake breeze front would make it, the interesting thing there is that is how that is difficult to answer because as the lake breeze front makes it further and further inland, because of all the heat flux that you're getting into that lake modified air, there is the tendency for the lake breeze front to kind of just wash out at some point. In terms of easily discernible lake breeze fronts, certainly to the longitude of Grand Rapids and further east of that. But as you get into environments that are supportive of them being further inland, those calm environments or even onshore large-scale flow environments, those are also the environments that tend to favor weaker temperature gradients and less convergence at the leading edge of that front. And those are the cases where you might have more of a boundary layer structure transition as opposed to a really well-defined front. In terms of the simulation work related to that, I didn't show the onshore flow simulations, but for those, we saw that it became increasingly difficult to detect the front, but you saw differences in the environment, and that there was a very slight temperature gradient, maybe a very slight convergence over this zone, and the convection was still developing inland of that. So there's could be something there, but yeah, getting a final, this is how far inland the front can make it, is a more diffuse question as a more diffuse front. In terms of where this goes with forecasting, I think it's more of that broader guidance of, in these conditions, this is what we've seen, and you might expect to look out for things like this. But very much open to continued feedback from the broader NOAA community and what could be useful and what products can we provide from the field campaign.
I think we're all out of time. If we could thank our speaker one more time, please. And thank you all for coming. We're going to lunch at Anna's house if anybody would like to join. Or have further discussion with Jason, but otherwise, thank you.
Thank you for having me.